Today we'll be going through the space chapter, which is essentially literally the second last topic of the syllabus already. You're going to learn about how the Earth rotates around the sun. You're going to learn about different positions of the moon that gives you different moons seen from the Earth, right? We're also going to learn about the only formula in this chapter, which is orbital speed. Basically, how fast the Earth is rotating around the sun, right? That is one of the orbital speeds, right? Then after that, we're also going to memorize the sequence of the planets using a very dumb thing. My very extreme mother just surface narcotics. So it's going to be Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, right? My very extreme mother surface narcotics. This is for you to remember the sequence of the planets, which I assume you may need to know. But once again, there wasn't enough past year papers because it just came out in 2023. So the only available past years are for February, March, May, June, and October, November. But after your batch, I'll have more. Then after that, yeah, we're going to learn about the most important thing in this chapter, which is the accretion model. The accretion model is basically saying how the planets and the galaxies and the solar system was formed, basically through the accumulation of dust, gas, and plasma, right? What happened was they started gaining and clumping mass together, right? And then eventually forming a star, and then started forming more planets around it. But I have a very interesting video to show you guys so that you have like a video in your head later on. And the second final thing we'll learn about is basically gravitational field strength and also elliptical orbits, which is basically saying that instead of Earth rotating around the sun in a circular motion, right, it's actually more an oval shape, like an egg, It's more oval shape than a circular one. So this is what they call elliptical orbits. Okay, so having said that, let's go through the first page here. The first page here basically says that Earth may go through different seasons based on the position it is against the sun, right? For example, oh, by the way, the reason why Earth has 4 seasons is because the axis of Earth, right, is actually tilted 23.5 degrees. Do you know what this means? 23.5 degrees. Basically, if before this, everyone assumed that, if this is the Earth's axis, right, we thought that the Earth will just rotate around this axis in a circular motion around the sun, right? But in reality, that was actually not the case. What happened was, right after that, they realized that actually Earth has a rotation axis of 23.5 degrees, meaning to say, with reference to the normal here is somewhere around 23.5 degrees, right? And Earth actually rotates around this axis instead, right? It will rotate around this axis, which is tilted 23.5 degrees. And because of this 23.5 degrees axis, right, rotational axis, this caused some places to experience relatively longer daytime and some places to experience relatively shorter daytime. For example, when Earth is at this position here, right, what happens is, right, the North Pole will experience 24 hours of sunlight, There will never be nighttime here. Because if you think about it, no matter how it rotates, this part is still facing the sun, right? So because of this, they will experience 24 hours of daytime. Alternatively, this South Pole here, right, will experience 24 hours of nighttime because no matter how this thing rotates, this thing will always be facing away from the sun. So this is the reason why it's like super, super cold and chilly during these kind of seasons here, right? And of course, we are somewhere around here, right? Nearer to the equator. That's why we experience relatively balanced daytimes and night times. Maybe it's like 12 hours of day and 12 hours of night. Even when there is at different positions, our maximum will face like maybe 13 hours of day and 11 hours of night, or vice versa, right? Because we are closer to the equator, our weather is very balanced and we will not go through any kind of the seasonal changes, right? So but the opposite will be true. If let's say Earth rotates around the sun all the way until this position here, right? just now, the North Pole was experiencing 24 hours of daytime, right? Right now, it will be experiencing 24 hours of nighttime. Alternatively, this part here just now was 24 hours of nighttime. Right now, it will experience 24 hours of daytime. So this is just a good to know. For in your exam, you just need to know that Earth will go through 4 seasons: autumn, winter, spring, and what did I say? Autumn, winter, spring, and summer. Yes, summer. Right. Because of the 23.5-degree rotational axis tilt. Okay. And if you look at the statements, everything is quite logical, which you already know. Earth rotates around its own axis once every 24 hours. That's why we experience daytime and nighttime, right? This explains why there is sun rising and sun setting. Earth rotates around the sun every 365 days. But this year, it will be 366 days because it's a leap year, right? And based on different locations, Earth is facing the sun, there will be a total of 4 seasons. Usually, the 4 seasons will be experienced relatively further away from the equator, right? Then you may experience summer, winter, spring, and autumn because of the relatively longer daytimes or the relatively longer night times the Earth will be getting. Okay. How come leap year there's extra days? Because usually February there's only 28 days. But this leap year, February will have 29 days. And that's why it's going to be 366 days this year. The year of the dragon, supposedly said by a lot of feng shui masters to be a very good year. Long年. Huh? You said huh? The name and shit. Okay, anyways, the moon will experience something similar as well. What's happening is the moon is actually not going to be a crescent shape, but it doesn't morph into a crescent shape. You all know, right? The reason why we can see the moon is due to the reflection from the Earth, from the sun to the moon, then back into Earth, right? So essentially, what happens is the sun will beam light onto the Earth, and the sun will beam light onto the moon, and then the moon will beam back light onto Earth. That's why we can see the moon, But based on different positions, because the moon obviously rotates around the Earth, right? Then based on different positions, it may receive different amounts of sunlight, right? And because it receives different amount of sunlight, what's going to happen is you'll see different moons during different seasons. Usually for Chinese, we call this the 满月, what is it called? 15, is it? They like to call it 15. It's basically like the halfway through the month, right? 15 is when you get the full moon here. Yeah, because all follow astrology. Everything follows astrology. Okay, so but so far in your exam, at least in the 2023 paper, I haven't seen them test your understanding on this. But I will assume you may need to know the different names of the moons. New moon, waxing moon, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, waning moon, waning crescent, and new moon. So then it will start repeating the whole process over and over again. So far there's no questions asking about the moon. So I can only assume it's just good to know only. Year 9? I don't know. I don't teach year 9. I don't know. But anyways, not so important on this part here. Do you remember the names of the different moon phase? I would like to say the answer is actually I don't know. But the reason why I put this here is because it was actually included in the syllabus of things that you should know. That's why I put it here. So if I were you, I'll bet on I need to memorize the names, right? So, but so far they haven't come up in the exam. So yeah, then next exam. But yeah, next exam they come out all this way. So my advice is if you're uncertain, just memorize all the names. It's not that hard, right? There's a pattern here. It goes from new to new, right? So it's waxing, then first quarter, last quarter, waxing, waning, waxing and waning, then after that full, right? So there's a pattern here. I can kind of memorize it on your own. But yeah, good luck. I don't need to memorize it. because I'm not using it. Okay, then after that, this next part here is basically a very straightforward one. If you think about orbital speed, is basically the Earth orbiting around the sun, right? Or the moon orbiting around the Earth, right? The moon orbiting around the Earth, right? And if you think about speed, speed by definition is distance over time, right? But since this is orbital speed, means to say it's moving in a circular motion, right? That's why the distance is 2 pi r, is essentially the circumference time, the time, which is the time taken to complete one orbit. Okay, so if you think about it this way, you don't actually need to memorize the formula. You just remember that orbital speed is circular motion. That's why the distance is 2 pi r, which is the circumference of a circle. Okay? Yeah. Can you guys try to attempt the 6 questions here? Attempt these 6 questions, and then we'll move on. The distance. That's the radius. These two things add together will be the radius. Yeah, for sure.
Okay, guys, are you done with reading?
Oh, okay. Let me repeat the orbital part. So basically, if you think about orbital speed, right, there's two components to it, right? Orbital means to say it's moving in a circular motion, and then speed is just speed lah. Since I know that speed is distance over time, right? Orbital speed is the total distance traveled in a circle, which is the circumference of the circle, right? In this case here, it will be 2 pi r. But the time, usually the time will be the time taken to complete one orbit. Right, so from here to here, how long did it take? Usually that is called the time taken. And thus it's called, that's why the orbital speed formula is 2 pi r over t. You get it now? Right? Anyways, anyone else that is not done? You're stuck now. What? Why? No lah, we got minus, bro. It's plus, bro. It says the Hubble Space Telescope moves in orbital speed. Its distance above the Earth's surface is 560 km, and the radius of Earth is 6,400. Means to say this is Earth, right? And then this thing is 560 kilometers away, but the radius of Earth is another 6,400, you know. So I have to plus these two together, what? Hey. And from here, you're just going to use the formula V equals to 2 pi r over t. In this case, here will be 2 times pi times the radius of then big 6,960 km. All right, over the total time, which is 96 minutes. Guys, in this question here, you do not necessarily need to change it into meters per second. Although if you changed it, it's fine. If you changed it into meters per second, you should get somewhere around 7,600 meters per second. If you don't want, you can just press everything into the calculator, right? And you'll get your answer in km per minute. Yeah, you can leave it like that. If they do not specify. Yeah, if they do, oh, it's so small, 4 point.
Times 10 to the power.
Times 10 to the power 0. Then it's just 4.7 only, right? 4.7 only, so little. I would think it's not correct. Yes. Wait, answer is 4.5, 455, not 4.5. Yeah, answer should be 455 or 456. 456 km per minute. This is radian. Wait, is this degree or?
What's the radius?
Wait. Oh, yeah, so it's 56, and the pedal.
忘记了，sorry.
Whatever lah. Anyway, it's 456. Okay. Now after that, the second one will be the same thing. Also, once again, they ask you to calculate the orbital velocity, which is once again the same formula, right? Which in this case here, you're going to write 2 times pi times straight away the distance, right? 384,399 divided by your time, which in this case here is 27.3 days. So whatever answer you get, will be in km per day, right? What will the answer be if it's km per day?
Yeah.
88500. Yeah, correct. Yeah.
French.
Correct, to three significant figures, it will be km per days. But if you left it, if you calculated in meters per second, just leave it, it's fine. Doesn't matter. Okay, then question number 3 is the same thing also. Right now, this one is km and this one is speed. They're asking you for the time taken, right? V equals to 2 pi r over t ma. Then t will be 2 pi r over v. Right, in this case here, it will be 2 times pi times 1000 divide. Oh, this one you have to change, huh? This one you have to change. Why? Why can't I just leave it in km for this one? Yeah, because the units are different. Then whatever answer you get will be in what? What units?
Second.
It will be in seconds. Yeah, press this in your calculator, whatever you get will be in seconds. Build a part. Link. Yeah. What is your unit meters per second, Chloe? You're looking for time, right? Shouldn't it be seconds? Or were you answering both my previous question? Yeah, okay. Okay, then finally, last question here for question number 5. 500 km per hour, this is obviously a velocity. Once per day, this is obviously a time, right? And they're asking you to find the radius, right? Distance from Earth, right? So V equals to 2 pi r over t once again. You're supposed to find r, so V times t over 2 pi is equals to your r, right? Which in this case here will be 500 multiplied by your time is per day, right? So it's 24 hours. The line break. Hello, are you guys still there? Your line broke. Let me repeat. You're supposed to use 24 hours because this is in km per hour. Then after that, just divide by a 2 pi, right? Then you'll be able to get your radius already. How much would that be? 1910 km. Okay, easy and straightforward. Okay, moving on next. The solar system. Dude, I said skip 4 and 6, bro. Oh my god, did I mute when I said that? GG. Sorry, my bad. I think I muted before I said that. So just skip 4 and 6, guys. That's not enough information. Okay, next we're going to talk about the solar system, which obviously everyone knows by now, consisting of the sun and many other planets, total of 8. There used to be 9, do you guys know? Sure. Yeah, there used to be Pluto here also, but after that it was demoted from a planet to a dwarf planet. Then after that, the solar system changed everything else. Okay, so anyways, like I mentioned, in terms of this solar system here, you would be expected to remember the sequence. You can remember the sequence using this very funny acronym, right? My very extreme mother just served us narcotics. By the way, anyone don't know what narcotics are? Drugs. Yeah, it's drugs. Right, so that's something to remember. Right, then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. I think some of you guys may have learned this in year 8 or 9. So most likely you guys remember the sequence already. That's nice, right? I do want to highlight one thing is that these 4 planets that are relatively closer to the sun they are known as the rocky planets, guys. They're actually more rocky. It means to say they're mostly made of rocky materials. Whereas these 4 planets that are relatively further away from the sun They are known as the gas giant planets, guys, because as the name suggests, they are mostly made of gas, right? That's why they're so gigantic. Okay, if you look at the statements here, besides the 8 planets, dwarf planets such as Pluto, asteroids in the asteroid belts, comets, and natural satellites orbit around the sun. The asteroid belt is in between Jupiter and Mars, guys. In between Jupiter and Mars here, there is something known as an asteroid belt, which is literally a whole lot of asteroids orbiting around the sun. Okay. Besides Earth's moon, there are many other moons that orbit the planets as well. Asteroids are made out of metals and rocky materials, while comets are made out of ice, dust, and rocky materials. I would put a little star on question number 4 here. If anything, I'm sure they will test your understanding on the difference between asteroids and comets, guys. So you probably want to know that. And finally, the 4 planets closer to the sun are rocky and small, where the other 4 planets are gaseous and large, guys, like I mentioned just now. Okay. Anyone has any questions with this part here? Should be fine, right? Quite straightforward. Okay. And this part here, which is basically the accretion model. The accretion model is one of the theories. And I say it's a theory because no one was there to witness it, right? But it makes a lot of sense. The accretion model is one of the theories that forms the solar system, guys. When I first looked at the accretion model, I was really confused because I was looking at a lot of words. And then after that, I tried to think about how to make it easier for you guys to learn. And thus, that is the reason why I included a YouTube link here. And let's watch it together right now. Yay, it's YouTube time. Everyone watch this, guys. It's very important.
Formation of the planets. The universe comprises countless galaxies, each one containing numerous stars. Around some of those stars, there are planets, just like those that orbit our own star, the Sun. The nebular hypothesis is the most widely accepted explanation for how the Sun and planets in the solar system may have formed. When our solar system was first created, all that was thought to have existed was a cold, spinning cloud of gas called the solar nebula. The nebula resulted from an uneven distribution of gases throughout the universe. As the gravitational pull began to condense the gas toward the center, the speed of the rotation increased. This caused the cloud to flatten, creating an accretion disk.
I want to highlight this part here, guys. So basically, they said that initially, before the solar system was formed, there was a lot of cloud and dust and shit around the space, right? So what happened was, right, because they were spinning, eventually all the mass start clumping in the middle. And because all the mass start clumping in the middle, you see this formation of the accretion disk. This purple color thing here that you see is known as the accretion disk, where most of the mass is already being spun to the middle. This example is basically like, you guys ever played or used a vacuum cleaner at home before? Nowadays, if you see the vacuum cleaners, they're all like the cyclone model one, right? Means when the dust comes up, the dust actually spins around in the cyclone format, right? It's very similar to this. You'll notice that the dust that go up your vacuum cleaner start clumping together, right? All the hair, all the dust, all the particles, all the start clumping together, right? This one is similar concept also. So what happened was, right, the mass and all the dust and everything started clumping in the middle. And I want you all to know that when mass increases, gravitational pull actually increases also. So it becomes a chain reaction, you know. The more mass it accumulates, then it'll generate a greater gravity, and the more gravity it generates, then it will pull more mass, and so on and so on and so on. Yes. Okay, continue watching, guys.
Matter continued to collect as the growing force of gravity drew it toward the center. Eventually, the gas warmed from the increasing pressure. As the mass further increased, the gravity also increased, and as a result, the temperature continued to rise. A ball of hot gas formed in the center of the accretion disk, creating a protostar, also known as the Sun. Finally, when enough gas gathered in the center of the protostar, the pressure generated enough heat to fuse the atoms, forming a star. Outside the star, matter was forming into clumps of gas, dust, and rock, which created protoplanets. These protoplanets continued to grow as they trapped material in their gravitational fields. Because the protoplanets all formed from the same cloud of gas and dust, they travel around the Sun in the same direction and in the same plane. The nebular hypothesis also explains how the planets are arranged. The heat and solar winds caused by the Sun swept the lighter gases farther out into the developing solar system. This is why the rocky terrestrial planets, Mercury, Venus, Earth, and Mars, are located closer to the Sun. The gas giants, Jupiter, Saturn, Uranus, and Neptune, formed in the cooler outer region of the solar system. The solar system continued to evolve even after its initial formation. Large asteroids slammed into planets, and the planets themselves differentiated into layers as they slowly cooled. Although the nebular hypothesis cannot be directly tested, it is a useful description for how a solar system forms. It explains why planets and the star they orbit usually spin in the same direction and lie in the same plane. It also explains the arrangement of the planets, with the rocky planets nearest to the Sun and the gas giants farther away. The next time that you look at the stars twinkling in the night.
Okay, that's all. Okay, just a quick recap. Basically, initially, before the stars were formed, before the planets and everything was formed, right, there was this thing known as the solar nebula, which was all the cloud, dust, and particles, right? Huh? Okay, okay, anyways, like I was saying, initially the solar nebula, right, consisting of cloud, dust, and particles and everything, right? Then after that, it started spinning, right? It started spinning, then it formed this accretion disk. This accretion disk started to gather more mass. Pay attention, it started accumulating more mass in the middle and eventually formed something known as a protostar. Protostar is this like baby, baby star. Then once it started doing fusion, right, then it turned into a real star, right? As this thing continues to spin, what happens was the mass start accumulating beside the protostar already, Then after that, these are basically the protoplanets. Then this accretion, this model explains why all these planets are spinning in the same direction, because essentially very, very, very long time ago, they were made of the same thing and they just kind of form into different formations, right? Right. And then, yeah, this part here also important. They say because of the solar flares, they kind of blew these light gaseous planets further away from the Sun, and the rocky planets actually stayed closer, right? And yeah, this was the summary of it. They orbit in the same speed, orbit in the same direction and in the same plane, and the gas giants are further away. Okay, anyone has any questions? Okay, yeah, all the relatively important notes I've already gone through the time to write down for you guys already, guys. If you look at this part here, accretion, the gradual increase in size of an object by buildup of matter due to gravity. Basically, it starts accreting and then started forming this here. An interstellar cloud is generally an accumulation of gas, plasma, and dust. I will assume they may ask you this. So you need to know what these interstellar clouds are made of, which is basically just gas, plasma, and dust. Okay, an accretion disk is a structure formed by diffuse materials in orbital motion around a massive central body. The central body is usually a star, which is a sun. Okay, Heat and solar winds from the sun swept the lighter gases further away into the developing solar system. Therefore, the rocky planets are closer to the sun. Okay. Yeah, everything that's relatively important I put down in notes already. Yeah. So just make sure you refer to this. Right. Yeah. Then after that, the gravitational field strength. This part is very straightforward. If I were to illustrate it in a poorly drawn format, if today you're standing right on top of Earth, right, you experience the greatest pull in terms of gravity. But as you go further and further away from Earth, let's say, for example, you try to shoot yourself into outer space, right? The further you are, as the distance increases, the gravitational field strength actually decreases. Which kind of makes sense, right? Because if you think as Earth like a magnet, the iron bar will actually be strongly attracted when it's close, and of course, if the iron bar is far away, it won't be attracted anymore, right? Gravity works the same way also. The further you are away, the smaller the gravitational field. If you want very strong gravitational field, you must be very close to the center of the Earth. Sorry? Yeah, inversely proportional, just like a magnet. Okay, this one, nothing much lah. You can literally think about it yourself and it makes sense. The last thing I want to talk about today before I throw you guys into the exercises is basically this elliptical orbits, guys. Elliptical orbits, there's two important things. Number one, instead of moving in the circular motion around the sun, it is actually the planets and all the moons and everything, right? They actually prefer to orbit in a more oval shape, known as elliptical orbits. In the elliptical orbits, they actually move in different speeds. When it is closer to the sun, the velocity of the elliptical speed is actually higher here, whereas the elliptical orbit speed is actually lower here. If you think about it, kind of makes sense, right? If you ever try to swing a rope on top of your head before, when it's closer to you, you feel that it actually moves much faster. Same concept here also, guys. Okay, that's the only thing you need to know for this chapter. Any questions, boys and girls? Okay, that's good. Come on. But I'm not looking at the question. Wait. Okay, if no questions, guys, you can actually start doing the questions below. That's going to be it for today. Already do the exercises, and if you have any questions, please make sure you voice out to clarify anything that you don't. All the way until you see 6.2, which is page 94. Then you stop. Yeah, and we will discuss next week. But if you have any questions right now, we can go through it straight away. Yes. Okay, everyone. Please start doing the questions right. Great. Name the force that causes planet move. Gravity lah, for sure. Right, gravitational force ma. Without gravity, the moon will just shoot out already.
Like when teaching that the different tiles is when there was no plan, you have invitation.
Yes, I used to say that too. Usually, the lighter planets. 这个是什么？这个是什么？这个是什么啊？So One. Down the road. Every single thing on it. One coil right now, I have like 2 or 3 or 4 or 5 coils. In this one turn. Oh, sorry, Chloe, I wasn't looking at the screen. Which one is 10C? Oh, this one, the calculation one. Okay, let's go through this question together before we end the day, since some of you guys may ask the similar question as well. So if you look at this question here, it says another astronaut is stationed in the ISS. The ISS orbits something about this. This is the radius. This is definitely the radius, right? And orbital speed of this amount. They ask you to calculate the number of orbits it makes in a day. So first things first is I want to know how long does it take for one orbit, which is t lah, right? So using the formula v equals to 2 pi r over t, right? I need to find t as 2 pi r over v lah, which in this case here will be 2 times pi times with my 6780 and then divide by my v, which is 7.66. Press this in your calculator and you'll get an answer in seconds. 5661 seconds. Confirm? Okay, so 566 seconds. This is no, you need to use the raw number for this one. Yeah, 5561. 5561 or 5661. Check your calculator. I see him almost every week. Yeah. Okay, give me a minute. I'm almost done with class already. 556, yeah, hey, it's 5561.
Okay.
5561. So this is the total time taken to complete one orbit, ma. And one day can have how many orbits? One day is how many seconds? How do I change it into seconds? Only 乘68了咩 ？Seconds 哦，2小时。Oh, how much is that? 86400. So this is one day. One day I have 86400 seconds, right? And one orbit takes 5,000 over seconds to orbit, right? Then just 86400 divided by your raw number, and you press that in your calculator, and you'll get the number of orbits per day.
Five on
5.
So,
Yeah, 15.5. 15.5 orbits in a day. 乘6. Yeah, just 15.5. Okay, guys, I want you all to finish everything else all the way until page 95. 94. Yeah. And then we'll discuss the answers next week. Okay, guys? That'll be it for today. I'll see you all next week. Welcome. Bye-bye. Okay, welcome. Bye.